In this last lecture for this week, I will briefly review the current direction of the field towards methods which go beyond post hoc explanation of the decisions of prediction models to building networks which are inherently interpretable by design, in other words, generative or causal models. We will also look at example uses of attention for disease modelling. Generative models will be covered in much greater depth in week 8. However, by way of a high-level explanation, they are models which extend from autoencoder networks to construct an underlying model from which novel examples may be generated. For example, variational autoencoders have an encoder-decoder type structure, but the latent space is modelled as a multidimensional Gaussian, which may be sampled from to generate new examples. This offers specific advantages with respect to building interpretable models, as it forces the model to learn to represent the whole image rather than just focus on the most discriminative features. In general, one big problem with classification and regression models is that they will disregard redundant or heterogeneous features when making their prediction. This is broadly true whether we're talking about penalised regression, decision trees, or deep models. And the reason for this is, since their sole objective is simply to predict the correct class or dependent variable in the case of regression, this means that if multiple features always appear together to explain the class, a model only needs to predict one of them to predict the outcome. For example, in this synthetic demonstration, a problem was set up where the diseased class has two subtypes, where each involves a feature in the centre of the square, but they also contain a second feature that appears in different locations in each group. The baseline class has no features. What you will find if you repeat this experiment is that classification-based methods only pick up on the central feature because that's all they need to make the prediction. For medical imaging, therefore, this is a problem, as clinicians often need the full picture in order to make prognoses or plan treatment. For example, for cancer monitoring, it is vital to pick up on all signs of the disease. So generative image-to-image translation models therefore offer a new way of visualizing these changes by requiring the network to learn how to switch an image from a diseased class to a healthy class. By doing this, in principle, the network has to learn all features of the disease in order to generate that image. One of the first examples of this was a paper by Baumgartner in 2018. This used a Wasserstein GAN to convert scans of brains from patients with Alzheimer's disease back to an intermediate state known as mild cognitive impairment. And in this way, the method was able to learn much more specific and high-resolution feature attribution maps, particularly when compared to GradCam, which you can see at the centre here. This has the problem of being constrained to the receptive field resolution of the output neuron, which is necessarily coarse. This new generative approach, on the other hand, was able to sensitively pick up on known features of disease, including hippocampal and ventricular atrophy. It does, however, struggle with more heterogeneous features of the disease relating to patterns of cortical atrophy. For that reason, your TA, Sherbas, proposed a new image-to-image translation approach which learns separate latent spaces for modelling class-relevant and class-irrelevant features. In the specific example of the brain, this means using a dedicated content space to model natural variation of brain shape and appearance, which is entirely normal and irrelevant to the Alzheimer's phenotype. Then, features specific to the disease class are instead learnt by a smaller attribute space, where these attribute encodings may then be swapped between images in order to change their class. By learning this bespoke model of brain variability, the model therefore becomes more capable of modelling heterogeneous features of both brain organisation and the disease phenotype, noting that patterns of cortical atrophy attributed to dementia are themselves variable across individuals. And this allows for the model to more sensitively capture all features of the disease phenotype, not just those needed to make the classification. For example, as shown here, where the features picked up by the model are compared against a ground truth map estimated for a sample from the ADNI dataset, which has been imaged longitudinally. However, arguably, inherently interpretable generative models do not go far enough. For many domains, what is needed more than detection of features inherent to a class is a causal model of how these features combine to create an instance of a class, specifically in the terminology of causal modeling, to create counterfactual examples which simulate whether by changing an example in a certain controlled way, it would, for example, change the class of the prediction. Therefore, over recent years, there have been attempts to build causal generative models structured around directed causal graphs, which model conditional relationships between the images and labels, under the assumption that specific combinations of labels cause the image to look a certain way, and further that certain labels themselves are conditioned on other labels. For example, let's consider face generation for one moment. The plausibility of a face generated with a moustache would clearly increase if the gender of the face was male. Therefore, following this logic, the creation of a generative model of faces should condition moustache generation on gender. Causal GAN was one of the first examples of this type of approach, which trained two generative models, one known as the causal controller, which builds a directed graph from a multi-layer perceptron, adding connections only between parent nodes and child nodes, i.e. from the top to the bottom of this graph, modelling the causal relationships between the labels. This causal controller is pre-trained and used to control which latent factor configurations to use in the generation of new images in the second stage. The second network is a conditional GAN, trained to produce plausible images with a sampling frequency which matches the conditional distribution sampled by the causal controller. And as such, it should not generate images which combine the labels female and moustache, and by the same argument, it should infrequently generate bald young men or men wearing lipstick. More recently, at this year's NeurIPS, a team from the Biomedia group at Imperial proposed a method for deep structural causal models. These extend upon the framework proposed by methods such as causal GAN to allow for image generation through variational inference using normalizing flows, where normalizing flows support generation of images under distributions that go beyond Gaussians. This is key for greater expressivity. Under all this, therefore, are modified variational autoencoders, which in this specific case model the causal relationship between age and sex, how these impact brain volume and ventricular volume, and thus together cause the total image appearance. In this way, they were able to generate images conditioned by specific choices of these labels and see the impact of modifying these choices on the total image appearance. In principle, therefore, these types of causal model offer significant potential to build mechanistic models of disease, with the very important caveat that for both causal GAN and this paper, the authors assume the causal graph structure is known a priori. Thus, this is only possible when a clear hypothesis of causal model for a disease or phenotype is already known. Finally, to finish, we have already seen examples from the architectures session on how attention models may be integrated into medical image segmentation to focus models on the most salient features for prediction. This improves prediction accuracy while at the same time offering model interpretability. But here are a couple more examples where attention is used to explain networks' decisions more comprehensively. For example, in this first case, the authors took a glimpse-based reinforcement style approach to attention and used it to explain networks' reasoning behind an Alzheimer's diagnosis. They found performance of the model outstripped a basic CNN, and that the features which were attended to agreed with known patterns of brain atrophy associated with the condition. And in this 2017 CVPR paper, attention was used to fuse CNN-based features learned from histology data with LSTM models of clinical reports to improve joint predictions whilst presenting saliency maps and language descriptions to justify the choices the network made. So, in summary, while saliency masking is an improvement on no information at all, it doesn't give enough information for comprehensive clinical diagnosis or prognosis. nor monitoring networks for failures. So this alone is unlikely going to be enough to see broad uptake of medical AI. Recent developments in the field have therefore started to look at inherently interpretable generative models, or better, causal explainable generative models, which go further to capture all features of disease and ideally build mechanistic models of cause and effect. At the same time, attention models remain important due to their capacity to both improve model precision and explain outcomes. As a tool which originally developed in the natural language processing literature, attention also offers potential for combining medical imaging with clinical reports. So that concludes this week's videos on interpretability. Please review the Keats quiz and I'll see you in the live session.